This is the AQA AS Physics. This is June 2009. This is obviously question 1. Now, what I've tried to draw on the board, I'm not quite sure if you can pick it up. Hopefully it works with a slightly better camera. Not much better. What we've got here is we've got the first column was just a dash because the second and third rows, the first isotope and the second isotope. The second column, number of protons. Third column, number of neutrons. The fourth column, is the specific charge. We've already got values that we're told. So the first isotope has 92 protons and 143 neutrons. We're not told its specific charge. It's the opposite for that. For the second isotope, we're not told the number of protons, we're not told the number of neutrons, but we are told the specific charge of 3.7 times 10 to the 7. Now, there's a little bit of a dot after specific charge, and that's because we've got to put the units associated with that, but I'll just draw it on the board later on because I can't bother. Okay, right, so 1A says, state what is meant by an isotope. Okay, now an isotope is basically, it's an atom which has the same number of protons proton number is the same but a different number of neutrons. You could also say this as the same proton number but a different nucleon number. Obviously the nucleon number is the number of protons and neutrons. Okay. Now the rest of this question pretty much just implies that going through the rest of these tables and all the different bits are filling in the unknowns. B part 1 simply says write in the table the unit for specific charge and over there basically. Now specific charge, just to reiterate for you, specific charge is equal to the charge per unit mass. In other words, the charge over the mass. Now generally they will refer, when we're calculating specific charge, they will refer to the nucleus. In other words, they won't include the electrons, because generally if you do, for most of atoms they're neutral, okay, so it has the same number of electrons as neutrons, so therefore it wouldn't have a specific charge at all. And also the mass is so insignificant of specific charge, it kind of doesn't matter anyway. Okay, that's just a point as well. If you are doing a question and it doesn't mention whether it's related to the nucleus or not, okay, you can just relate to the nucleus and say, I'll include the charge of the electrons, but because the mass, I won't include the charge or the mass of the electrons because it's so insignificant, but it will generally always be asking about the nucleus. Okay, so B part 2 says, in the above table write down the number of protons in the second isotope. Okay, well as I say, we just wrote down in 1A that proton number is the same but a different number of neutrons for an isotope, and this is the first and second isotope. We assume to them be of each other, okay, quite clearly, so therefore the number of protons should be 92, okay, because it's the same as the first one. Okay, and I mean it's only worth 1 mark, so you should think, well, it should be quite obvious, okay, and that's asking about the number of protons, not neutrons. Hopefully you spotted that, but it doesn't matter if you didn't come to you straight away. You're going to fail, doesn't matter. Anyway, apart from that, 1B part 3 says to calculate the specific charge of the first isotope and write this in the table. So basically we've got to calculate this bit. Now, as I mentioned, specific charge is charge over mass, okay? So you might, as I say, want to look in your formula book, but you should know that the charge of because the only thing we're considering here is the number of protons, okay, and neutrons. So the only charge we're considering is the number of protons, okay. So the charge of a proton is 1.6 times 10 to the minus 19. In other words, the positive of the electron charge, okay. And obviously there's 92 of them, so there's 92 lots of that charge. However, the mass, well, the mass of a proton, the neutron, are so similar. Because the mass of a proton, I think, is 1.673, and the mass of a neutron is 1.675. Might be getting them the wrong way around, but the shorthand is that both can be said to be 1.67 times 10 to the minus 27, So basically, it's 92 plus 143, and as they both have pretty much the same mass, for what we're considering anyway, because we've rounded up the charge to such a rounded figure, we can round up everything else as well. So anyway, times that by 1.67 times 10 to the minus 27. Okay, and as I say, just in case now, subbing that into your calculator, you should get a answer of approximately great, I haven't calculated, that's brilliant. Sorry about that, I thought I wrote it down, but obviously I hadn't. Just on the calculation, gone, that'd be enough. So, yeah, that did give you a good point actually. You do need to do calculations in exams. I generally don't, but you know, if you want to pass, you might have to. Okay, so anyway, sorry, that's just me waffling because I forgot to type it in, so I'm just trying to waste a bit of time. 7 times 10 to the minus 27. Now I do apologise if this isn't quite right. I don't think it is. Sorry. Yep, that's looking a bit better. Okay. Sorry, one sec. That's not the best, is it? Sorry about that. Yeah, so as I say, it's just subbing the numbers into your calculator. Sorry. Okay, so it's obviously your 92. I'm sure I've probably. I'm sorry, I just had to go and do something. You know, contacts, everything. So 92 times 1.6 times 10 to the minus 19. Over 92 plus 143 times 1.67 times 10 to the minus 27. Okay, and that comes out to be 3.7 times 10 to the 7. Well, 37.6 times 10 to the 6. Okay, so you set that's your specific charge, and you have to remember, that is, because it's charge over mass, we measure charge in coulombs, okay, and it's coulombs per mass, okay, per unit mass, and mass in kilograms, so it's coulombs per kilogram, okay. I'm sorry, I'm not sure, probably should have mentioned that. So in part B, part 1, it did ask you to put that in your heading of your table. It's coulombs per kilogram. So sorry if I didn't mention that, and obviously that's what you mention this as well. Okay. B part 2 is a little bit different. It says calculate the number of neutrons in the second isotope. So we're going to use the same formula, except this time we're not given the total number of neutrons and protons. We're just given the specific charge, and obviously because it's an isotope, it has exactly the same number of protons. Okay, so we kind of work backwards in the sense. Okay, so as I say, we know. I would again label, this is for B part 4. I would label again that you've got the specific charge is charge per unit mass. Okay, and then I would sub in what you currently know. Now, obviously on the top is going to be exactly the same. It's 92 times 1.6 times 10 to the minus 19. However, on the bottom, because you could say, oh, it's 92 plus a number, I will just leave that number as, well, in algebra, you might argue you could put x. I'm just going to put a letter that represents a number, so I just label n. So it's n times 1.67 times 10 to the minus 27. Okay, because obviously it's going to be a certain amount, a given number of protons and neutrons times the mass of them, which is 1.67 times 10 to the minus 27. And we know, because we're told in the table, that's equal to 3.7 times 10 to the 7. Okay. So then again, it's just rearranging. So you times both sides by n, divide both sides by 3.7 times 10 to the 7. Okay, so in other words, you replace n with 3.7 times 10 to the 7, and vice versa. Okay, so then what you end up with is 145. Oh, what's it? Redo this. So it's 92 times 1.6 times 10 to the minus 19 over your 3.7 times 10 to the 7 times your 1.67 times 10 to the minus 27, and it gets you 238. Now it says 0.22, but I just leave it as 238. Now that's not the number of neutrons, that's the number of protons plus neutrons, remember? Okay, and we know the number of protons is 92, so 238 minus 92 is the number of neutrons, okay, because as I say, it's the number of protons and neutrons, because we assume them to have the same mass, because the mass is so insignificant when it's separated between the two. Okay, so 238 minus 92 is 146. So there's 146 neutrons, and you fill it in the table. Okay, that's the end of question 1. I think that was quite an easy question to be able to do. It's just rearranging, excuse me, rearranging the specific charge equation, and to be honest, you should be really quite familiar with that. And it's quite a nice 10 marks you should get. But as I say, if you didn't know what an isotope was, you would be quite stuffed, okay? So, just shows you it's quite key to understand what an isotope is, but really that's GCSE kind of knowledge, so hopefully it wasn't too bad. Alright, so thanks for watching, and we'll see you in the next video.